Beneath the deserts of western China, something enormous is happening. A machine the size of a skyscraper is drilling deeper and deeper. Not for oil, not just for gas, but to reach a part of Earth humans have never touched before. 10,000 meters below the surface. What exactly are they looking for? Imagine Mount Everest, 8,149 meters high. Now go deeper than Everest is tall. This is the frontier between human ambition and the planet itself. Heat, pressure, time, all stacked against us. And yet, down we go. China is drilling 10,000 meters into the Earth. Here's why. Take a breath, then follow the drill. In 2023, China began drilling an ultra-deep borehole in the Tarim Basin. The site sits in China's northwest, within one of Asia's harshest deserts. Announced by China National Petroleum Corporation, the goal, past 10,000 meters. That's deeper than Everest is tall. This is not an ordinary oil well. It is one of the deepest scientific drilling projects in Asia. The drill passes through multiple continental rock layers. Rock formations here are over 145 million years old and older. Each meter is a page in Earth's hidden archive. Geologists read color, grain, mineral signatures like a language. This region is known for violent sandstorms. Extreme heat builds with depth. Massive pressures push back against the bit. Crews work in shifts. Precision never sleeps. Sensors, telemetry, and models guide every decision. On the surface, order. Below, a labyrinth of rock. Samples become datasets, then stories of deep time. Human lights against ancient darkness. The threshold is crossed. Ultra deep. Beat. Now, why drill this deep at all? Why drill this deep? Why commit years of effort and billions in investment to pierce 10 kilometers into the Earth's crust? The answers are as layered and complex as the rock itself, driven by two fundamental human pursuits: scientific discovery and the quest for energy. Let's begin with the science. 1. To read the Earth's deep geological history. Deep underground, shielded from the erosion and chaos of the surface, lies a pristine chronological record of our planet's past. Each layer of sediment is a page in a stone library, preserving the story of millions of years. We can trace the ebb and flow of ancient climates, identifying ice ages and periods of intense global warming. We can find evidence of ancient oceans that once covered what are now the driest deserts on Earth. And we can pinpoint the exact moments of ancient catastrophes, volcanic supereruptions, asteroid impacts, and mass extinction events that reshaped life on this planet. The deeper the drill goes, the further back in time we travel, accessing chapters of Earth's autobiography that have never been read before. 2. To understand the mechanics of our living planet. The Earth's crust is not a static shell. It is a dynamic system of tectonic plates, constantly shifting, grinding, and building pressure. This project aims to drill into one of the most complex geological settings, the Tarim Basin, where ancient continental plates collided. By placing sensors deep within these formations, scientists can listen directly to the stresses and strains building up along fault lines. This isn't just about understanding past seismic activity. It's about mapping the forces that will trigger future earthquakes. The data gathered from these depths, subtle changes in pressure, temperature, and rock properties, could revolutionize our models of seismic forecasting. The goal is to move from simply reacting to earthquakes to one day, perhaps, anticipating them with greater accuracy. Improving earthquake prediction, even by a small margin, could save countless lives. The science is profound, but it walks hand in hand with a powerful industrial driver. 3. The search for ultra-deep oil and gas. For over a century, we have extracted hydrocarbons from relatively shallow reservoirs, but as these reserves deplete, the industry is forced to look deeper, into geological frontiers that were once considered unreachable. The Tarim Basin is believed to hold vast, untapped reserves of oil and gas, locked away in formations under extreme heat and pressure. Finding and accessing these resources is a monumental challenge. It requires technology that can withstand conditions more hostile than the surface of Venus. But the potential reward is immense, a significant boost to a nation's energy security. This well is not just a scientific instrument. It is a high-stakes exploration probe, testing the limits of engineering to unlock the energy that powers our modern world. Every meter drilled provides critical data on the location, quality, and accessibility of these deep Earth resources. And finally, 4, to explore future energy sources. The deeper you go, the hotter it gets. At the target depth of 10,000 meters, temperatures are expected to soar above 200 degrees Celsius. This natural heat radiating from the Earth's core is known as geothermal energy. While this well's primary goal may be hydrocarbons, the data it collects on the geothermal gradient, how quickly the temperature rises with depth, is invaluable. Understanding these deep Earth temperature profiles is the first step toward harnessing geothermal power on a massive scale. It's a clean, virtually limitless energy source waiting to be tapped. Projects like this one are, in effect, drawing the maps for the energy infrastructure of the future. A future that may rely less on burning fossils and more on harvesting the innate heat of the planet itself. So, why are they drilling? They are drilling for knowledge, to decode the planet's ancient climate and protect us from its future convulsions. They are drilling for resources, to secure the energy that fuels our present. And they are drilling for innovation, to unlock the clean energy that may power our future. It is a mission where geology meets geopolitics, where scientific curiosity meets the stark realities of energy security. Each motivation is powerful on its own. Together they create an irresistible force, compelling humanity to push the drill bit deeper and deeper into the great, dark unknown. 10,000 meters. It's a number so large it feels abstract. To comprehend the scale of this descent, imagine taking Mount Everest, the highest point on our planet, and plunging it into the Earth's crust. Beat. You would still have more than 1,000 meters left to drill. This is not just digging a hole. It is an engineering odyssey into a realm of unimaginable pressure and heat, a journey that pushes the very limits of our technology and our resolve. Only a few countries have ever attempted such a feat of ultra-deep drilling, each project a testament to national ambition and scientific curiosity. The most famous of these is the Kola super-deep borehole in Russia. For over 2 decades, Soviet scientists drilled relentlessly, reaching a staggering final depth of 12,262 meters. It was a monumental achievement, a vertical voyage that shattered our understanding of the crust. But it also revealed the profound difficulties. At that depth, the rock behaved less like a solid and more like a plastic, and temperatures soared to 180 degrees Celsius, far hotter than predicted, hot enough to melt their equipment and halt progress forever. The lessons learned at Kola were written in broken drill bits and melted steel. Today's rigs are a different breed. They are marvels of engineering that automate what once depended on the brute force and intuition of roughnecks. Every operation, from connecting pipe segments to managing downhole pressure, is orchestrated by a symphony of sensors and algorithms, all designed to outsmart the abyss. At the very tip of this 10-kilometer-long spear is the drill bit, the focal point of the entire operation. These are not simple tools. Special diamond drill bits, forged under extreme heat and pressure, are designed to battle the relentlessly abrasive rock formations deep within the Earth. The cutting edge is made of polycrystalline diamond compacts, or PDCs. These synthetic diamond cutters are fused to a tungsten carbide substrate, creating a tool that can withstand the crushing forces and intense friction that would pulverize ordinary steel. They are engineered to resist the incredible heat and abrasive wear generated as they chew through granite, schist, and quartzite, layer by ancient layer. But even these super hard materials have their limits. When a bit dulls, it must be replaced. This process, known as tripping, involves pulling the entire multi-kilometer drill string out of the hole, section by section, replacing the bit, and running it all the way back down. A single trip can take days and cost a fortune, a stark reminder that progress is measured in increments, punctuated by long delays and hard-won breakthroughs. As the bit descends, the environment becomes increasingly hostile. For every kilometer down, the temperature rises by about 25 degrees Celsius. At 10,000 meters, the drill operates in a furnace exceeding 200 degrees. These are temperatures that can degrade conventional steel, warp instruments, and melt the very lubricants that keep the machinery alive. Every component, from the simplest seal to the most complex sensor, must be made of exotic, heat-resistant materials designed to survive conditions that defy earthly logic. And it's not just the heat. The lithostatic pressure, the sheer weight of 10 kilometers of rock, is immense, exerting over 1,000 times the atmospheric pressure at sea level. This pressure wants to crush the borehole closed. The sensors that act as the driller's eyes and ears must not only survive this onslaught, but stay impeccably accurate under the most extreme thermal and physical stress imaginable. This is where measurement while drilling, or MWD, becomes critical. A suite of sophisticated electronics housed just behind the drill bit constantly streams vital data to the surface. It transmits the wellbore's precise orientation, inclination, and azimuth, ensuring the path is true. At the same time, logging while drilling, or LWD, uses gamma ray detectors, resistivity tools, and neutron porosity sensors to read the properties of the surrounding rock. This data paints a detailed, real-time picture of the invisible geology, allowing scientists to navigate through ancient strata and identify targets of interest. The drill string itself is a paradox, a structure of immense strength that is also perilously flexible. Over its 10-kilometer length, even a slight imperceptible bend at the surface can translate into a significant deviation deep below. If not corrected instantly, the well can spiral out of specification, missing its geological target by hundreds of meters and compromising the integrity of the entire project. Control is therefore constant, careful, and calm. Every decision is guided by the stream of data from below. The unsung hero of this entire operation is the drilling fluid, or mud. This is no ordinary liquid. It's a complex engineered cocktail of water, clays, and specialized chemicals, precisely formulated for the conditions downhole. It performs a dozen critical jobs at once. It cools and lubricates the fiercely hot drill bit, cleans the hole by carrying rock cuttings back to the surface, and most importantly, it balances the immense pressure of the surrounding rock, preventing the borehole from collapsing. But sometimes, the earth pushes back. A sudden influx of high-pressure gas or fluid from a formation, known as a kick, is one of the most dangerous events in drilling. It's a signal that the well is about to lose control, and it demands instant, flawless decisions. This is where layers of engineered safety stand between control and chaos. The primary defense is the blowout preventer, or BOP, a massive stack of high-pressure valves that can shear through the drill pipe and seal the well in seconds, containing the pressure and averting a catastrophe. As the well deepens, it is reinforced. Sections of heavy steel pipe called casing are lowered into the hole, and a specialized cement slurry is pumped down to fill the annular space between the steel and the rock. This process doesn't just support the wellbore, it isolates different geological zones, preventing fluids from migrating between layers. The cement locks the steel casing to the rock, creating a permanent, fortified conduit to the deep earth, holding the line against unimaginable forces. Even with a straight hole and stable pressure, the dynamics of the drill string itself present a constant threat. The immense length of pipe can twist and release like a rubber band, causing the bit to stop and then violently spin free. This is called stick slip. Another danger is whirl, where the bit or string begins to rotate eccentrically, like an unbalanced washing machine, hammering itself against the side of the borehole. These destructive vibrations are monitored in real time, and advanced control systems make micro-adjustments to RPM and weight on bit to mitigate them before they lead to equipment failure. This is a marathon, not a sprint. Ultra-deep wells take months, sometimes years, of continuous 24-hour-a-day operations. The deeper you go, the slower the progress becomes. The geology gets harder, the temperatures higher, the risks greater. In this unforgiving environment, the last 1,000 meters can take as long to drill as the first 9,000. Endurance is not just a human quality, it is an integral part of the engineering design. Every component is built for longevity, and a rigorous schedule of preventive maintenance is the only thing that averts catastrophe. You must find and replace the weak links before they fail. Another day, another meter. The rhythm of the rig is one of relentless patience. Beat. But with every meter drilled, a question hangs in the air. What waits below? Each core sample brought to the surface is a message in a bottle, a fragment of a story billions of years in the making. The possibilities are stacked like the strata themselves. Now the mystery begins to unfold. Fossilized microorganisms, signatures of ancient seas, ancient marine layers trapped far from today's shores, hydrocarbon reserves, if the rock is right, evidence of past climate shifts, hotter, colder, wetter, drier, clues to how continents formed, how Earth's crust behaves and breaks. Do mantle heat pulses leave fingerprints in deep strata? Tiny inclusions can preserve oceans older than mountains. Each ultra-deep well rewrites a line in the textbook. What if that reflector is a buried shoreline or an ashfall? The deeper we go, the less we assume, and the more we realize how little we understand. Quick pause. If you're loving deep science, tap subscribe and the bell. Like, share, and drop your wildest drilling questions below. Feet. Back to the deep. Porous layers can unlock reservoirs if sealed just right. A spike in gas, then questions race in. Sometimes the lab cheers before the field does. Traps, seals, timing, the classic puzzle now miles deep. Whisper, but what about the rumors? Let's separate story from science and keep the mystery without the misinformation. Because the truth is strange enough. Down we go. Conspiracy versus reality. Next. Some say they're hiding something or searching for a secret energy. Even they discovered something dangerous. Beat. But officially, this project is scientific and industrial. There's no evidence of anything supernatural, just hard problems and harder data. When humans drill into the deepest parts of Earth, we enter a world shaped by unimaginable pressure and time. That's mystery enough. And the work continues, meter by meter. No monsters, no portals, just evidence and patience. Curiosity asks better questions than fear. Hypothesis, test, revise, repeat, results, not rumors. Soft. Let's talk feats and firsts, what this project has already achieved, and what it unlocks next. We rise to see the bigger picture, then go deeper again. In the vast, unforgiving expanse of the Tarim Basin, a monumental feat of engineering has been achieved. A recent well, a testament to human ambition, reached a staggering depth of approximately 10,910 meters. To put that into perspective, it's like stacking Mount Everest on top of itself, and then drilling down through both. This accomplishment marks it as Asia's deepest vertical well, a direct, uncompromising plunge into the planet's crust. Drilling vertically presents a unique set of gravitational and geological challenges, demanding perfect alignment and immense power to overcome the sheer weight of the drill string and the crushing pressure of the Earth above. Every meter gained is a victory against forces that are difficult to comprehend. The temperature at this depth can exceed 200 degrees Celsius, hot enough to cook the very electronics sent down to gather data, while the pressure is over 100 to 300 times that at the surface, an environment more hostile than the deepest ocean trench. The journey to this incredible depth was not a sprint, but a grueling marathon of persistence and problem-solving. It took over 580 days of continuous, round-the-clock operations. Beat. More than half of that time, nearly 300 days, was spent on the final, arduous stretch, drilling from 8,000 meters down to the final target. This is where the Earth truly begins to fight back. The rock formations become older, harder, and more abrasive, slowing progress to a crawl. The drill bit, spinning miles below the surface, encounters unpredictable shifts in geology, from brittle granite to plastic-like salt layers that can squeeze the borehole shut. Each day was a battle of inches, a slow, methodical advance into a realm of extreme heat and pressure, where a single miscalculation could mean catastrophic failure, trapping millions of dollars of equipment forever in the deep. Along this journey, a string of remarkable records was shattered. The project achieved the deepest borehole imaging in Asia, sending sophisticated acoustic and electrical sensors down to paint a picture of the rock layers in unprecedented detail. It also secured the deepest core samples ever retrieved on the continent. These physical cylinders of rock, painstakingly cut and brought to the surface, are tangible pieces of Earth's ancient history. And in a seeming paradox, The operation also set a record for the fastest drilling rate on land for a well beyond 10,000 meters. This wasn't about raw speed, but about sophisticated efficiency, a testament to the advanced technology that, once past the initial hurdles, could perform with surgical precision even in the most extreme conditions. To see where no one has seen before, the team deployed advanced deep cable imaging tools. Lowered on a wire line kilometers long, these instruments didn't just look, they listened and felt. Using acoustic pulses and electrical resistivity measurements, they effectively painted the borehole's inner walls, creating a detailed 360-degree log. This digital painting reveals the secrets of the strata, the precise angle of the rock beds, the presence of tiny, hidden fractures that could channel oil and gas, and the boundaries between different geological epochs. It's the closest thing to having eyes at the bottom of the well, turning a dark, inaccessible hole into a readable library of geological information. But drilling the hole is only half the battle. Securing it is just as critical. To ensure the well's long-term stability, tailpipe cementing at these unprecedented depths was required to seal its structural integrity. This involves pumping a specially formulated cement slurry down the drill pipe and up the narrow space between the steel casing and the rock wall. At over 10,000 meters, the extreme temperatures and pressures can cause ordinary cement to set too quickly or fail to bond. The engineers had to develop a complex chemical cocktail that would remain fluid long enough to be pumped down, yet set with immense strength to prevent the well from collapsing and to isolate the different rock layers. It is a high-stakes, one-shot operation that locks the architecture of the well in place, forever. Perhaps the most significant milestone is not what was found, but what was built. Over 90% of the critical components used in this project were domestically developed in China. This represents a monumental leap in technological sovereignty. From the advanced polycrystalline diamond compact, or PDC, drill bits capable of chewing through the planet's hardest rocks, to the sophisticated measurement while drilling systems, this project was a showcase of homegrown innovation. This strategic independence reduces reliance on foreign supply chains and cultivates a powerful domestic industry, ensuring that the knowledge and capability gained here can be replicated and advanced for future projects, both within China and globally. At the heart of the operation is an automated 12,000-meter class rig, a marvel of modern engineering that orchestrates the entire workflow. This isn't just a machine for drilling, it's a robotic system. It automatically handles the heavy, dangerous work of connecting and disconnecting kilometers of drill pipe, a process that once required large crews in high-risk positions. The system's precision and power are essential for managing the immense weight and torque involved in ultra-deep drilling. Inside the control cabin, far from the rig floor's noise and danger, human expertise merges with artificial intelligence. Sophisticated algorithms constantly analyze a torrent of downhole data: vibration, temperature, pressure, and torque. They intelligently balance the rate of penetration with critical safety margins, pushing the drill as fast as possible without risking a catastrophic failure like a stuck pipe or a blowout. This digital brain anticipates problems before they happen, making real-time adjustments to keep the descent smooth and safe. Efficiency in such a remote and harsh environment is paramount. The rig and its supporting systems are designed with modularity in mind. This allows for entire components to be swapped out quickly and safely, minimizing downtime. Under the extreme desert conditions, where sandstorms can halt work and temperatures can swing by dozens of degrees in a day, this ability to rapidly repair and reconfigure is not a luxury. It is a fundamental requirement for success. The technology sent into the well must survive a truly hellish environment. All downhole electronics are hardened for extreme heat and shock. Components are housed in vacuum-sealed flasks, insulated with advanced materials, and designed to withstand violent vibrations as the drill bit pulverizes rock. Every circuit board, every sensor, every connector is a small miracle of engineering, built to function flawlessly under conditions that would instantly destroy conventional electronics. The ultimate prize of this scientific endeavor is the rock itself. The cores retrieved from the deepest sections of the well penetrate formations older than 500 million years from the Cambrian period. These are rocks that were formed when complex life was just beginning to flourish in the oceans. They are a time capsule holding direct evidence of Earth's ancient climate, atmosphere, and tectonic activity, long before the dinosaurs, before the great forests, from a time when this desert was a vast primordial sea. By combining these precious core samples with the data from the wireline logs, a comprehensive ultra-deep stratigraphic profile of the Tarim Basin emerges. For the first time, geologists can see a continuous high-resolution record of the region's history, layer by layer, spanning hundreds of millions of years. This complete column of rock is a Rosetta Stone for understanding the basin's formation and its resource potential. This wealth of new information is invaluable. The data fuels critical research in geology, helping to refine models of plate tectonics and continental evolution. It drives geochemistry studies, analyzing the chemical fingerprints in the rock to understand the origin of oil and gas. And it informs geothermal studies, mapping the Earth's heat flow to assess the potential for clean, renewable energy. And the industrial implications are profound. Based on the data gathered from this and other deep wells, significant land-based oil and gas resources below 10,000 meters have been identified in this basin. These ultra-deep reservoirs were previously considered unreachable, but this project proves that they are now within the grasp of technology. Those deep intervals don't just represent new resources, they expand the entire frontier of exploration. They force a re-evaluation of what is possible, opening up similar deep ancient basins around the world to new scrutiny and potential development. This single well has redrawn the map of energy exploration. The benefits ripple outwards. The engineering advances pioneered here in automation, materials science, and data analytics will inevitably spill into the broader drilling industry, making operations safer, smarter, and more efficient everywhere, from conventional oil fields to geothermal projects and carbon capture wells. This project is also a powerful engine for human capital, training a new generation of subsurface scientists and engineers. Young researchers are gaining hands-on experience with world-class technology and unique geological samples, building the expertise needed to tackle the next generation of scientific and energy challenges. The impact is felt on multiple scales. The local industry benefits from the massive investment and logistical support required for such an undertaking. And at the same time, so does our global understanding of the planet we live on. Every discovery made here contributes to the collective knowledge of humanity. In the end, it all comes back to the source. Every watt of power consumed, every algorithm run, and every data point analyzed traces its purpose back to the rock miles below. It is a relentless quest to understand the story written in stone. But to unlock those secrets, the team must first survive the surface. Now, we explore how they endure the formidable challenges of the Tarim Basin itself. Here, in one of the world's largest and driest shifting sand deserts, nature sets the rules. There is heat above and heat below. On the surface, summer temperatures soar past 40 degrees Celsius, while the ground itself can become hot enough to fry an egg. And then there is the sand. Fine as dust, it is carried on the wind and finds every seam, every joint, every opening, threatening to clog delicate machinery and electronics. In the face of sudden, violent sandstorms, everything must be tied down, or it will be gone. Survival here is a constant state of vigilance and preparation. And at night, as the heat radiates away into the clear sky, the desert is silent, but it is intensely, watchfully alive. Logistics thread across long distances to keep the rig alive. Steel, chemicals, sensors, each time to the hour. Storm windows dictate when to move and when to brace. Tie down, cover up, power off non-essential circuits. Safety is a choreography rehearsed daily. Medical readiness stands by for heat and fatigue. Toolbox talks align everyone on the plan. Permits and lockouts prevent cross-wired tasks. Hydration is protective gear in this heat. Infrared checks catch failures before they cascade. In dry air, static can be a spark too many. High-vis and lighting keep motion visible. Shale swelling and fracture gradients set mud weights. Casing strings reinforce the borehole like bones. Bond logs verify the seal holds. Managed pressure drilling trims the margins safely. Flow tests are measured, contained, and monitored. Every bolt check keeps the tower steady. Out here, resilience is the real resource. One last descent, then the big picture. Beneath the deserts of China, a hole 10,000 meters deep reaches into Earth's history. Not to awaken monsters, not to open portals, but to understand the planet we live on. Because sometimes the greatest mysteries are under our feet. Pages of deep time finally opened. If this journey moved you, subscribe for more ultra-deep science. Like, share, and explore our next documentary right here. Soft. We'll keep listening to the Earth, from the surface to the deep. Thanks for watching. See you in the next descent.